So I wanted to spend a little bit more time here just going over the interpretation of results. So as we've seen, even with R, all statistical software packages produce redundant information. Now, for the purposes of this course, I could reasonably expect you to calculate a t-statistic, and what you've got really is two sort of sub-questions beyond this, and this should be a convenient thing for me to ask if I was setting a written exam, which of course I'm not this year, but it's also something I might set for coursework. So there's two sub-questions that apply here. Firstly, is the variable in question significant? And if the variable is significant, if the variable increases, does the probability here either increase or decrease? I.e., this is just the same as reading off if the thing is significant, if the sign of the random variable is either positive or negative. So it is there liable to be a lot easier than it might seem at first, and there is a lot of repetition here compared to the first lecture. But if you look at the point 2 there on the slide, there is the word probability there, so strictly speaking these are slightly different in terms of the interpretation because these are probability regression models. So the y variable here relates to a probability, and there is a marginal difference in terms of the interpretation, but this is only a marginal difference. So for this regression model then, so that's the small table of t-statistics that's produced in this case, and exactly as we saw before, it's the second row downwards that is the interesting part of this table. So if you go to the far right hand side, the thing is significant because you've got 3 asterisks there, and it says in the far right hand side on the second row that the p-value is less than 2 times 10 to the minus 16. If you scroll now all the way to the left, the estimated coefficient for load is minus 0.0015484, so this is negative. So that's how you work it out, going from right to left. And now to interpret this in the Queen's English, you go from left to right. So the coefficient of load is negative and statistically significant. So as load increases, the probability of success decreases. And then what I've got there below that is a sort of hand calculation example, which is be relevant if there was going to be a formal written exam for this module. Of course, this year the assessment will be computational coursework. Okay, but there's just some practice hand calculation example there just to show you where the results come from. And what you've got there is the thing is bigger than 2, so the p-value is less than 0.05, and if you're doing it correctly, the two inequality signs point the different way. So it's almost an exact carbon copy of the regression examples that you've seen before in terms of the interpretation and the t-statistics, etc. However, because these are probability regression models, there is a very tinsy-wincy bit difference. So in the interpretation, really, when you're writing this down as it's shown in this slide, you should recognise that these are probability regression models, not just bog standard ordinary least squares regression models. Okay, so here we've got, since the coefficient of load is negative and statistically significant, as load increases, the probability of success decreases. So I perhaps wouldn't be malignant enough if this was a handwritten exam to dock marks if you said what is on the slide without the probability bit, but certainly for the coursework I would expect you to have the probability bit, precisely because you want the surety of the interpretation and nailing down of the technical detail. And it's good practice, I think, here, because anybody marking your work should be confident that you know what you're doing and you're interpreting results in exactly the right way. And here it's worth just making extra clear if there's any doubt that this is a probability regression model, so there has to be a probability bit in terms of the interpretation, as is shown there at the bottom of the slide. So for the probability regression model, so remember there's this sort of subtlety in terms of the interpretation. You'd expect similar models to give you similar results on any reasonable data set. So pick out the useful bits of the regression output in R, this table of t-statistics, which we've done at the top of the slide, and it's the second row downwards that is the interesting bit. So work it out going from right to left. write it down in the Queen's English going from left to right. So from the second row, the thing is significant because you've got 3 asterisks to denote significance, and then the p-value is less than 2 times 10 to the minus 16. Scroll all the way to the left. The estimated coefficient is minus 9.488 times 10 to the minus 4. So write this down in the Queen's English as the coefficient of load is negative and statistically significant. So as load increases, the probability of success decreases. Again, the probability bit, extra interpretation, it's a probability regression model. Then there's an example at the bottom of the slide of the hand calculation of the t-statistic, similar to an exam type question. So I'm not going to go through this in so much detail, it's just that when you calculate the thing, because it's bigger than 2, the p-value is less than 0.05, and if you're doing this correctly, these two inequality signs should point the different way. So in terms of the precise interpretation then, so for the exam, the coefficient of load is negative and statistically significant. So this means as load increases, the probability of success decreases. And try and make sure, if you had a question on this, that you emphasize that there is a probability bit here. So it's important that it says there probability of success decreases, not just the success decreases. Now, there are some subtleties here which I wanted to try and get across as best as possible in terms of the interpretation. So beyond just passing the exam or the coursework, what you're always looking for with these things is 2 different sources of information telling you the same thing, cross-checks. And it's always worth cross-checking numerical information like this with the graph. Now that might sound absolutely boneheadedly, stupidly simple, okay, but it really isn't whenever you're doing practical project work. Okay, and these things are often very different compared to when you let loose on a real data set, when it matters that you get the right answers, compared to when you're just sitting an exam that somebody is pre-prepared for you. And also, I wanted to re-emphasize this sort of interpretive aspect here, that you'd expect the logistic regression models and the probability regression models to give you similar answers on a realistic data set. So we're looking then for an extra graphical cross-check of the numerical information we've got before. So what we're going to do here is plot the data as a sanity check. Now again, this might sound completely trivial, and of course it is with modern software, but this can be a big deal whenever you've got practical data examples. So I've worked as a research fellow and a research assistant in the past, and this, I can promise you, is a big deal when you've got proper data. So what we've done here is calculate the proportion of failed items. So that's where you've got the first line from. Proportion is the number of failures divided by the number of items tested, and then the second line you're plotting the load against the proportion. The result is shown in the graph on the slide, and what you've got there is very clear evidence that the failure rate increases as the load increases. So this both makes good physical common sense, that as you put these aircraft components under more strain, they are more likely to fail. It also matches with the interpretation of the logistic regression model and the probability regression model. So you've got there 3 bits of information telling you the same thing, 2 statistical regression models and this graph. Also, the examples you're likely to see in this course, there's an intuitive explanation behind the findings. I wanted to give some extra calculation examples. So you're asked to calculate the load for which there is a corresponding 50% failure rate. So if the failure rate is 50%, then it must be also that the success rate is 50%. So for the logistic regression model, from the output, so the fitted regression equation is the log of the probability over 1 minus probability equals 5.3397115 minus 0.0015484 times the load. And I just wanted to write it out in full there so you can see what this table of t-statistics and the estimates etc really mean in terms of the estimated equation. Then all you would do is put in the value of p equals 0.5. So if p is 0.5, 1 minus p is 0.5, so p over 1 minus p is 1, take the logarithm, you get 0, so that's where the 0 equals 0.53397,115 minus 0.0015,484 times the load comes from. Solve for the load, and you should get this value here at the end, 3448.535 kilograms. Now, if this number is reasonable, what you should see is that if you do the same calculation for the probit model, then you should get a similar answer. So for the probit model, if you're asked the same question, for what value of the load is there a 50% failure rate? So since the thing either succeeds or fails, this must imply then you've got a 50% success rate. So we've got the snippet of the regression output there, and then from the output, the estimated equation is that the z to the minus 1 of the probability is equal to the regression equation. So again, I just want to show you how the regression equation relates to this table. So what you've got is 3.271 minus 0.009488 times the load. So from the tables, if you look at them, you've got the z of 0 is 0.5, so this implies then that z to the minus 1 of 0.5 is 0. So that's coming from the bit at the top of the slide that the success rate is 50%, so the probability P is 0.5. So again, you've got similar looking calculation to the previous slide. So 0 equals 3.271 minus 0.009488 times load, rearrange, and you're getting at the very end there a very similar answer to the previous slide. So again, similar models give you similar answers, and for the probit model, you've got an estimate of the load being 3447.513. In terms of the summary of the lecture then, so we've discussed big data and small data examples of logistic and probit regression models in R. So the big data example is potentially quite dangerous in this case, as in this case a technically incorrect model gives very plausible looking results. Okay, so I think this is the first example where I've taught something on a module and your basic intuition can lead you astray. So this is not technically the right analysis, but it serves as a useful teaching prelude, and I'll go through the technically correct analysis and a professional standard analysis and solution to this problem in the lecture next week. So the data set, it turns out, contains additional structure which you can make full use of using the techniques in the next lecture, building on what we've covered this week and the previous week. For the big data example, we had 3 categories, so 2 regression equations to describe the whole system. You could use a multinomial regression model for multiple categories, but the modelling and computation is harder and more involved, and I don't think there's really much benefit in this case. The second example that we've just gone through with the aircraft component shows that probability models in R work neatly for small sample problems. Okay, and with the adjustment we show you next week, also work very nicely for practical industrial problems as well. There to my textbook, and we will finish off this little bit of the course in the lecture next week.